Alright, hey, hello everyone. Can I first of all check if everyone's able to hear me? Alright, cool. Yeah, I guess I'll just wait another minute or so for other people to arrive, and then I guess we'll get started. Alright, hey, hello everyone. Alright, I guess before we start then. Yes, hello everyone. So I'm Raymond. I'll be presenting the second half of the Math2501 and 2601 revision seminar. So I'll be covering the second half of the course, so going on to eigenvalues and eigenvectors, and then also with the Jordan forms. So I guess yeah, so I'll be monitoring the chat, so if any of you guys have questions, just make sure you put them in, and I'll try to answer them when I see them. Yeah, so I guess the typical question is are these slides going to be put online? Is this being recorded? So yeah, like the slides will be put onto the MathSoc website probably like tomorrow or the day after, and the video should itself be recorded so you can just review it from the YouTube channel. Okay, so yeah. Okay, so first off, we're looking at eigenvectors, eigenvalues, and eigenspaces. I guess I'll probably focus a bit more on the second half of this, well, like I guess the very last section, because I assume you guys are less familiar with that, and most of you are probably quite familiar with eigenvalues and eigenvectors, given you've done some class tests on it already. Okay, so if we have a vector space and we have some sort of linear transformation on this vector space to itself, then we can have this idea of eigenvalues and eigenvectors. So like T has to map from V to V. It doesn't make sense if it's mapping somewhere else. So eigenvalue is, so if we have a certain vector such that when I apply this transformation to it, the answer I get is just a scalar multiple of the vector I put in, then I can say that vector here is an eigenvector, and the lambda value here is the eigenvalue of T. And since we know that any linear transformation can also be represented by a matrix, I can similarly define eigenvalues and eigenvectors. Oops, I should keep that consistent. Let's make that V. I can similarly have eigenvectors and eigenvalues for matrices. Pretty much exactly the same thing. Okay, so the set of eigenvalues of T is the spectrum of T. Just definition. Invariance, we're not really going to look at this much, but so we say that a subspace is T invariant. That's saying that it means that if I have any element that is inside this vector subspace U, if I apply the linear transformation to it, then it turns out that the answer itself lies within U. So saying if I have a vector in U and I apply transformation to it, it would still be inside U. That just means it's T invariant. Okay, so now some properties of eigenvectors, eigenvalues, eigenspaces. Well, I guess like one of the things about this course is that there's like a huge amount of content, and you guys probably know that it doesn't seem really feasible to like just memorize every single formula if you don't really understand it properly. So I guess like what I want to do here is sort of like have like a slightly intuitive understanding of like each of these points, so you can try and sort of remember them without just like entirely memorizing. Most of these are like fairly similar and should sort of make sense. Okay, so well, the first line here, that's just from our definition of eigenvalues and eigenvectors. And in terms of the second line here, so this is saying like what's the eigenspace? Well, as eigenspace, remember that's the set of eigenvectors for a corresponding eigenvalue. So like if I have an eigenvalue of lambda, this is saying the eigenspace is the set of all vectors such that T of V is equal to lambda of V. Well, how do I find them? Well, that's the same as saying T of V. Oops. Let's get rid of that. That's the same as saying T of V minus lambda of V equals to the 0 vector. And well, that's the same as saying this. Well, I guess they reverse it around, but it doesn't really matter. If I take the negative, it's still 0. So like, this is why we can find the eigenvectors corresponding to an eigenvalue by looking at the kernel of lambda I minus t. Or similarly, for a matrix, we'll have lambda I minus a. Right, so like this thing here, I can rewrite it as t minus lambda I. And let's get rid of that. T minus lambda I times v equals to 0. So we're basically just looking at the kernel of lambda I minus t, and we can find the eigenvectors. Well, I guess like maybe previously you guys have been doing like t minus lambda I. Well, it's the same thing. T minus lambda I is probably easier because if you have a matrix, it's easier to do the matrix minus lambda I compared to lambda I minus the matrix. But yeah, like that's just where this comes from. I I guess a small distinction between like the eigenspace and eigenvectors is that, remember, 0 is not considered to be an eigenvector. Earlier in definition we said that eigenvector is a non-zero vector. So technically the eigenspace itself, like this, includes 0. So the eigenspace is really the set of eigenvalues corresponding to this eigenvalue lambda, in addition to the 0 vector. Okay, and eigenspaces are T invariant. So in the last slide we said that T invariant means that if I have something in U, then when I apply this linear transformation to it, it's still inside U. So eigenspace being T invariant means that if I have a vector that's inside the eigenspace, and then I apply T to it, it will still live inside the eigenspace. Well, that should make sense, because we've been saying that an eigenspace is where we have T of V equals to lambda of V. And so it should make sense that if I have so like the eigenspace here is basically spanned by this by the vector V. So like when I apply V to it, well, lambda V here is still inside that eigenspace. Or a way you can think of it is if I apply T to this again, so if I apply T to this, well, this is again an eigenvector, so I'll just get lambda squared. So when I apply T to an eigenvector, that's just saying that the answer I get is still an eigenvector, because it's simply a scalar multiple. Okay, so I guess like that result should also sort of make sense. It's not really something that you just need to memorize, it should make sense. And next we're saying that if lambda and mu are distinct eigenvalues of this linear transformation, then the eigenspaces are actually, well, the only common element to the eigenspaces is the 0 vector. And again, this should make sense because, well, if we say that lambda is an eigenvalue, that's saying T of V is equal to lambda V, and similarly we can do it with mu. But like, given an eigenvalue, if I apply the linear transformation to it, I'm going to get like some fixed answer. Like, it's either lambda or mu. It can't be like both at the same time. Like a single vector can't be both. Well, I guess like T of V can only equal to lambda V, or it can equal to mu V. It can't equal to both of them at the same time. I should say or. So it's either equal to lambda V or mu V or something else. It can't be both at the same time unless if V is the 0 vector. In that case, these two things can be equal. So like that's why like the eigenspaces themselves don't have anything in common except for the 0 vector. Okay. The next thing is, if V is finite dimensional, then a basis of V consists of eigenvectors of T, if and only if T with respect to B is diagonal. I guess we'll talk about that a bit more later. We won't worry too much about it for now. Okay. So in terms of other properties, so a matrix A, again, this is it's a square matrix. All of this discussion of eigenvalues and eigenvectors is only relevant for square matrices. So saying the matrix is diagonalizable. Diagonalizable meaning that we can write it in the form of this. So diagonalizable means that there exists some sort of matrix such that when I write it in this form, it's equal to a diagonal matrix. Yes, that's what it means to be diagonal. So D only has got terms on the diagonal. I shouldn't say 0, it has some terms on the diagonal, which actually are the eigenvalues. And I guess like one of the semi-important things to remember is like the order that they're placed in. So I think the first P over here, I've got the inverse, but the second one is like not the inverse. Like sometimes you might incorrectly try to write it the other way around. Like technically it is true that there does exist a matrix P that satisfies this first equation as well. Like you could write that. But actually, the standard form is the one you should remember, because it turns out that if you write it like this, then P is actually a matrix of eigenvectors. So P would actually be the matrix of eigenvectors, whereas if you write it in this form, then P inverse is the matrix of eigenvectors. And it's like a bit more confusing. So I guess this is the form that you should have it in. Okay. Yeah, well, I guess you could also write another form. I could move the P's and the P inverse to the other side, and I can say like A is equal to P times D times P inverse. That's okay as well. Okay. So a matrix is diagonalizable, so I can write it in this form if and only if it has. My phone notification keeps going off. Yeah, I think that might actually have been from my computer. Let me just turn that off. Yeah, hopefully it should be gone. Alright, so yeah, so a matrix is diagonalizable if and only if it has n linearly independent eigenvectors associated with it, which is of course in general not true. You guys have already looked at Jordan forms. That's sort of like a generalization. Any matrix can have a Jordan form, but not everything can be diagonalizable. So it's diagonalizable if and only if it has n linearly independent eigenvectors. And in fact, we know that distinct eigenvalues correspond to linearly independent eigenvectors. Well, I guess like earlier we've already seen that the eigenspace is sort of like the span of like a vector. So if we set the eigenvectors and the eigenspaces only have the zero vector in common, then it should probably make sense that well, they're linearly independent. So I guess like from 1 and 2, we can say that any matrix or any linear transformation that has n linearly independent eigenvectors, anything that has n distinct eigenvalues will automatically have n linearly independent eigenvectors and be diagonalizable. So if we have n distinct, okay, I'm not going to write that out, but if we have n distinct eigenvalues, then it should be diagonalizable. But if a matrix doesn't have n distinct eigenvalues, it may or may not be diagonalizable. In order to work it out, you would actually need to work out the corresponding eigenvectors and see if you have any linearly independent. Right, so I guess like that's quite important. So having n distinct eigenvalues guarantees it's diagonalizable, but not having n does not say anything about whether it's diagonalizable or not. Okay, so number 3 over here is just saying that eigenvectors and eigenvalues don't depend on the basis. Like I can change the basis and I should have the same eigenvalues. And the eigenvectors are, well, I guess the eigenvectors are the same, they're just represented differently because we're in a different basis. But that's about it. Alright, so then we have the idea of multiplicities. So the eigenvalues of a matrix are given by the solutions to the characteristic polynomial, which is obtained by solving this. Again, I guess like in your lectures, you might have seen it written as like lambda I minus a instead. Really like these just give the same thing. Determinant equals to 0, whether I look at a minus lambda I or lambda I minus a, you get the same values for lambda. But the one written on the slide here is like easier for you to calculate. Okay. Yeah, so I guess like what's the logic behind this? Well, just from before we said that from here, eigenspace looking at the kernel of lambda I minus t, which comes from the definition. So that's precisely where it comes from. So basically by solving this equation, I can find all the values for lambda that are eigenvalues. Okay, and then so we know that the determinant is a degree n polynomial. So we know that from the from the first year algebra, you would know that any degree n polynomial has exactly n complex roots if you count multiplicities. So like those sort of multiplicities is the algebraic multiplicity. So it's saying what is the multiplicity of this root lambda in the polynomial equation. So obviously all of the algebraic multiplicities added together should equal to the degree of the polynomial. That's from first year algebra. Whereas the geometric multiplicity is the dimension of the eigenspace associated with lambda. So remember the eigenspace, we said that that is the kernel of a minus lambda I, and so the dimension of that kernel is the geometric multiplicity. And in general, we know that the geometric multiplicity is greater than or equal to, is less than or equal to the algebraic multiplicity. So I also know that geometric multiplicity is always greater than or equal to 1. That's important as well. That's just saying that any eigenvalue would in fact have an eigenvector. Right, so the dimension of the geometric multiplicity is the dimension of the eigenspace that's at least 1. There's at least like one factor that expands the eigenspace. And yeah, the algebraic multiplicity is larger than or equal to that. Okay, so a matrix A is diagonalizable if for every eigenvalue lambda I, we have the geometric multiplicity being the same as the algebraic multiplicity. So I guess like this is very similar to the results that we saw earlier, right? Like earlier we said that a matrix is diagonalizable if and only if, we're saying that, yeah, it's diagonalizable if and only if it has n linearly independent eigenvectors. And now we're saying that, well, if the geometric multiplicity is equal to the algebraic multiplicity, well, that's just saying that if I add together all of the geometric multiplicities, I should get n, which is because that's the sum of the algebraic multiplicities. And then if the sum of the geometric multiplicities, that's just saying that the eigenvectors actually span the entire space. Or in other words, we have n linearly independent eigenvectors, and so it will be diagonalizable. Okay, so I guess I can try some examples. So here we've got 4 matrices here. I'm not going to skip over probably some of them. I'll just look at a couple of these examples. So typical exam question, find all the eigenvalues and eigenvectors that correspond to these matrices here. Okay, so first one over here, well, one way you can do this is to actually solve the equation, the determinant of a minus lambda I equals to 0. So you could try to do that. So like I could subtract lambda I from here, and then set the determinant equal to 0 and try to solve. So I can set the determinant of this thing equal to 0 and then try to solve for lambda, which is, well, it's typically okay because well, it's a quadratic equation. I guess you guys can all solve that pretty easily. You could do that if you want. I don't think there's anything wrong with it. Sometimes there are things that might make it easier. So it turns out that the sum of the eigenvalues is actually the trace of the matrix. Remember, the trace just means the sum of the diagonal terms. So 1 and 4. And the determinant we know is, well, it's 1 times 4 minus the product of negative 1 and 2. So that's one way you can do it. We can have the sum of the eigenvalues being the trace, 1 plus 4, and we have the product of the eigenvalues being the determinant. And here you can find what they are by inspection, or you can construct a quadratic equation. Let's say lambda squared minus 5 lambda, that should be 5 lambda plus 6 equals to 0. That's just from, well, sum and product of roots. And then you can solve for lambda quite easily from that. I don't know, some of you might find that slightly easier than using the characteristic polynomial. Well, I guess they're both pretty easy. Okay, so like once we know what the 2 eigenvalues are, then we can try to work out what the corresponding eigenvectors are. So we just need to, so remember the eigenspace is found by looking at the kernel of a minus lambda I. So for lambda equals to 2, we're going to look at the kernel of a minus 2i, right? So we're going to look at a minus 2i. So 1 would now become negative 1, 4 would now become 2. And so looking at this kernel. And then pretty much like you can just find a vector very easily, just choose one that works. So basically this is just saying that the first coordinates times negative 1 plus 2 times the second coordinate needs to equal to 0. well, in that case, 2, 1 works. So like this is my eigenvector, and the eigenspace is just the span of this vector 2, 1. And we do exactly the same thing for lambda equals to 3. So I find a minus 3i. I get this matrix and find the kernel. So I just need to find a vector that gives me the 0. It gives me the 0 vector when I use this matrix on it. And clearly the vector 1, 1 works because negative 2 times 1 plus 2 times 1 would be 0. Okay, and then I get like 2 eigenvectors. Well, of course, eigenvectors are not unique. I can have any other multiple of these ones and there will still be eigenvectors, but we just need to choose one. And I guess like these are some natural ones that, well, I guess they look nice. But yeah, there's other choices that you could use. Alright, I guess that second example here is pretty much the same, so I guess you guys can look at it afterwards. I'm not going to go through it. And the third one is pretty much the same as well. I guess the only comment on this one is that we have non-real eigenvalues. I mean, there's non-real eigenvalues. Well, I don't know, it might look a little bit confusing because it doesn't really seem like this is a matrix that that actually has like a non-trivial kernel, but actually it does. Well, in this case, like, I guess like probably second row is easier. Oops. So we probably look at the second row and then we can guess that, okay, well, 2i and 1 would work because 2i times negative 1 plus 1 times 2i would give me 0, so that does work. And then in case you're worried, you might want to check it by multiplying the first row of the matrix by our vector. 2i times 2i will give us negative 4, and then 4 times 1 will give us 4. If I add them together, that will give me 0. So yeah, indeed, this is an eigenvector. It works. Yeah, already you could just use the original matrix and multiply it by it. And yeah, then we get the other one as well. Okay. So, I guess the fourth one here is a little bit trickier. This is a 3x3 matrix. So it's so the rule we talked about earlier, we're using the trace being the sum of the eigenvalues and the determinant being the product of the eigenvalues. This still applies. But the problem is that well, the determinant is not necessarily so easy to calculate, or even a characteristic polynomial is generally not very easy to calculate. This example itself is a bit easier because there are quite a lot of zeros, so we can actually use the expansion to calculate the determinant for this matrix. And you get this, so this is the characteristic polynomial, and then you can solve for lambda to obtain these values. This is one way you could do it. There is an easier way to do it, which is actually by inspection. So if you look at this matrix, there are quite a lot of zeros here. So it's probably not hard for you to realize that if I take lambda to be 2, then a minus lambda I would give me this thing being 0, and this being 1 and 1. And so sort of just by inspection, you would realize that well, obviously 2 is an eigenvalue, and in fact 2 must have an eigenspace that has a size has dimension of 2, because the matrix that we get has 1 1 1 1. That matrix would actually have a kernel of dimension 2. So like pretty much just by looking at it, I would be able to conclude that lambda equals to 2 is an eigenvalue with an algebraic multiplicity of at least 2. So AM is at least 2. And then using the trace, I would be able to work out what the other eigenvalue is. So I think for this question, you can probably just like look at this matrix, notice there are lots of zeros, and you can guess what the eigenvalue is. And that would be a lot less work. You'll be able to find everything in like 2 minutes. Whereas you can do this characteristic polynomial business and you get this one. It should always have it should always be chosen in exams so that the roots are nice. You can use your high school methods to try to solve this cubic equation and get the roots. But yeah, it just takes a little bit more time. And besides, like once you calculate it, you will have to well, we still need to look for the eigenvectors. So the same process as before. I'll do a minus 2i and find the eigenvectors associated with it. So let me just write that out. a minus 2i, we have 1, 1, 1, 1, and everything else is 0. 0, 0, 0. Okay. And we just need to determine eigenvectors for this. So I guess like this one you have to be a little bit careful, because looking at this, you should realize that this is actually a matrix with a kernel that has a dimension of 2. So actually choosing one eigenvector is not enough. We actually need to choose 2 eigenvectors. And so usually you can just like guess like random ones. Well, not really random, but you can like construct ones that would work. Like obviously we see that the leading column here is all 0, so that well, if I choose a vector that's 1, 0, 0, this should always work, right? But what I mean by work is that when I multiply the matrix by 1, 0, 0, I should always get 0, 0, 0. So that 1, 0, 0 obviously lies in the kernel of this matrix. So I'm just going to choose that one first. And then I want to choose another one. So in that case, I don't care about the first coordinate anymore. Let's just make it 0. And then for the second and third coordinates, well, all I need to have is the second and third coordinate being the negative of each other, because then when I multiply the matrix by my vector, I would get 0. So let's say we just choose this, and that works. I guess in the answers here, you choose 0, negative 1, 1, doesn't matter. Both of them would work. Okay, and similarly we do it for lambda equals to 4. I'm not going to go through that, but you should get this vector. Okay. So find the algebraic and geometric multiplicities of each of the above matrices. Well, I guess like for all of these, we already solved the equation for the eigenvalues. Like here we've got 2 distinct eigenvalues. Well, each of like from the characteristic equation, this is the characteristic polynomial is a quadratic. So we've got 2 roots. Each of these roots have an algebraic multiplicity of 1, because they're not repeated roots. And we know that the geometric multiplicity is always less than or equal to the algebraic multiplicity. Well, then that means that the geometric multiplicities must both be 1. And that's the same as these ones, because they all have 2 different eigenvalues. And finally, this one here, we observe that we have 2 different eigenvalues. We have got 2 and 4. So in terms of algebraic multiplicity, we will say that 2 has an algebraic multiplicity of 2 because it appears twice in the root. It's a double root. And 4 would have an algebraic multiplicity of 1, and hence a geometric multiplicity of 1. But in terms of eigenvalue 2, we need to figure out whether its geometric multiplicity is 1 or 2, because it could be either 1. And in order to figure that out, well, actually we already worked it out, because we worked out that for lambda equals to 2, we actually have got 2 corresponding eigenvectors. Right? And that's not generally true. It's possible that you only have 1 eigenvector. In this case, we actually have 2 eigenvectors, which means that the dimension of that eigenspace is 2. Sorry, the dimension of the eigenspace is 2, which means that the geometric multiplicity is also 2. Right, so I guess like that's the only one you really need to be a bit careful about. If the algebraic multiplicity is larger than 1, then like the geometric multiplicity could be multiple values, and you have to check carefully which one it is. In this case, it's 2, because we have 2 linearly independent eigenvectors for lambda equals to 2. Okay, so this is what we get here. So in general, the GM is less than or equal to the AM. In this case, they happen to be equal. Okay. So for the next question over here, for each of these matrices, we want to calculate the algebraic and geometric multiplicities for each one, as well as like finding all the eigenvalues and eigenvectors, without calculating the characteristic polynomial. It's basically, well, these are 3x3 matrices. You generally don't want to do the characteristic polynomial. It's a huge amount of work. It will probably take you way too much time. So you should always try to find some other method. Okay, so I guess like in terms of the first question, we're given the eigenvalues. Well, we're given 2 of them. If we know 2 of them, we can always find the third one very easily. because we know that the trace of the matrix is the sum of the eigenvalues. So we have 2, 8, and -7. If I add those up, that would be 3. And if I add together the two eigenvalues I already have, that would be -1. So obviously the last one I would have to be 4. Assuming I did that correctly in my head. But like, yeah, I'll work out what the last eigenvalue is. I'm not going to go through calculating the eigenvectors. It's the same as what we did on the previous slide. But automatically, because I have 3 distinct eigenvalues, I would know that all of them have an algebraic multiplicity of 1. Right? Because this is like a 3 by 3. So the algebraic multiplicities have to add up to 3. So if I have 3 distinct, each of them must have an algebraic multiplicity of 1. And then we know that geometric multiplicity has to be less than or equal to the algebraic multiplicity, and so they must also be 1 for all of them. So okay, question 1 is easy. All of them have algebraic multiplicity of 1 and a geometric multiplicity of 1. Question 2 over here is, well, I guess another similar sort of thing. This time we're given 2 eigenvectors instead. Well, if we know the eigenvectors, then we can find what the eigenvalue is simply by multiplying d by these vectors. So, okay. If I multiply d by these vectors, you can do this yourself. You will find that the eigenvalues we get are 3 and 1. And then again, we can look at the trace of the matrix. So I can look at the trace of this matrix, and that would be the sum of the eigenvalues. And I already have 2 of the eigenvalues. So using this matrix, I can now work out what the third eigenvalue is. And we work out that it's actually 4. And again, since the 3 eigenvalues are actually distinct, that means that the the algebraic multiplicity is 1, and the geometric multiplicity is less than or equal to that, so it must also be 1. Like that. Okay. Alright, so next thing we have conditions for diagonalizability. So we've said that diagonalizable means I can write it as a product of a I can write it as if I change the base, it would be a diagonal matrix. So T is diagonalizable if and only if there is a basis for V consisting of the eigenvectors of T, and that's equivalent to saying V is a direct sum of eigenspaces of each of the eigenvalues. And I guess like number 4 here is the important one, which is the sum of the geometric multiplicities is the dimension of V. Or another way of saying this is actually like all of the geometric multiplicities equal to the algebraic multiplicities. Okay. So I guess like this is an example. We're given this linear transformation here, and we are asked, is there a basis for which the matrix of T with respect to this basis is diagonal? Well, this is really just asking, is this matrix diagonalizable? Because diagonalizing a matrix is just like changing the basis to using the eigenvalues as using the eigenvectors as the basis, in which case it will be diagonal. So, well, we said that it's diagonalizable if and only if the geometric multiplicities actually match the algebraic multiplicities. So that's all we need to do here. So first I would write the linear map with respect to this basis with this v1, v2, and v3. Okay, so I'll do that. Basically saying that where did I get this matrix from? Oops. This is just saying when I apply v1, so this is saying t of 1, 0, 0. Right, if I use v1, v2, v3 as my basis, then 1, 0, 0 would be v1 with respect to this basis. And so this is saying that if I apply t to 1, 0, 0, then the answer I get would be 2, 1, 1. And with respect to this basis again. And so that would mean that if I can just do the same thing for v2 and v3, and this would be the matrix to represent this linear map. And what we have here is that we can again use the characteristic polynomial. Here it's fairly easy to calculate the characteristic polynomial because we have all of these zeros here, so I can just use the expansion of the determinant to get this one, and clearly I get these values for lambda. Those are just the roots of this equation. So clearly lambda equals to 1 has a multiplicity of 1, whereas lambda equals to 2 appears twice, so it's got a multiplicity of 2. So I guess now what we need to do is we want to look at lambda equals to 2. That's the one that's tricky. We want to look at whether lambda equals to 2 has a geometric multiplicity of 1 or a geometric multiplicity of 2. That's what I want to work out. If the geometric multiplicity is 2, then the matrix will be diagonalizable. But if the multiplicity is only 1, then the matrix is not diagonalizable. So that's what we do. We consider A minus 2i. So we're trying to find the dimension of the kernel. And we get this matrix here. And this matrix shows that, well, the kernel has a dimension of 1. So in fact, the kernel is spanned by the vector 0, 1, 0. And so the geometric multiplicity, when I add them together, is actually only equal to 2. It's not 3, so it's just saying that it does not span the entire space, and so it's not diagonalizable. Okay. They look at a special case of some real symmetric matrices. It turns out that these ones have some nice properties. So one of the properties is that all of the eigenvalues are real. That's very important. All of the eigenvalues are real. And in fact, eigenvectors corresponding to distinct eigenvalues are orthogonal. So they're not just linear independent, they're actually orthogonal. And so previously we said that we've got the P inverse A times P is a diagonal matrix. That happens if we have n linearly independent eigenvectors. But in this case, we actually have an orthogonal matrix. So saying that all of those columns in Q are actually orthonormal. Right? Remember, orthogonal matrix means that the columns are orthonormal. So the columns of Q form an orthonormal basis for the vector space Rn. Okay. So I guess this is simple example. We're going to diagonalize this matrix given the characteristic polynomial. So just like before, we have the characteristic polynomial. We can solve for that equal to 0, and we can get all of the eigenvalues and eigenvectors. I'll just skip over this. We've gone through this a lot of times. We have the eigenvalue and the eigenvector for all of these. And clearly in this case, we have distinct eigenvalues and eigenvectors. And this is how we diagonalize it. So remember we said that P inverse A times P equals to D. Or another way of saying this is that A is equal to P times D times P inverse. That's exactly what's happening here. So the diagonal matrix is formed by having the eigenvalues. So in this case, we have the eigenvalues being, why is that highlighted? Okay. My eigenvalues are -1, 3, and 1. My diagonal matrix is -1, 3, and 1. And then in terms of my matrix P, so the matrix P is the matrix of eigenvectors corresponding to these eigenvalues. So we worked out that -1 has an eigenvector of -2, 0, 1. And so this column here is -2, 0, 1. It's an eigenvector corresponding to this eigenvalue. And we similarly do the same thing with the other ones. So the eigenvalue of 3 has an eigenvector of -3, 1, 1, like so. And then this one here is just the inverse of that matrix. Usually if the question asks you to find the matrices such as diagonalizable, you can just leave it in this form. Finding the inverse is of course very annoying, and multiplying them all together is also very annoying. You shouldn't need to do that in your exam. Normal operators, since it's a bit short on time, I think I'll just skip through that. Okay, so next thing we have is on conic sections. So previously you might have seen like simple conics, like if I don't have this xy term, then generally you know that we might have a hyperbola, or maybe we might have an ellipse, or in some special cases maybe a circle, something like that. Well, this is like a more general equation. So anything in this form, then I can actually try to draw this, but it's in order to draw it, one of the ways we can do this is to like simplify it by rotating the axes. So first of all, I guess this is all like the process for doing these questions. Like first of all, we just need to write this into a matrix form, and this is how it's written. You can try expanding this, and you will find that you get the same equation. So these two are actually the same equation, just written in a different form. You might also think that there's like multiple ways that you can actually write the matrix in the middle. I didn't actually have to choose B and B to be the two diagonal entries. I could have chosen like 2B on the top right and then 0 on the bottom left. You could do that, but then the matrix doesn't necessarily have eigenvalues, or doesn't necessarily have real eigenvalues. But it turns out that it does in this case. It should always have real eigenvalues because it's a symmetric matrix. Okay, so like pretty much this is just the method. You can probably just like memorize this is the method that you should do whenever you see a question of this form, which is to let x equal to q of t times xy. Well, I guess like what this means, remember we said that a matrix is diagonalizable with an orthogonal matrix. That was the spectral theorem we saw earlier. Okay, that's too far back, but yeah. Normally we have Q inverse, but remember for an orthogonal matrix, Q inverse is the same as the transpose. Equals to Q transpose. And that's why it's Q transpose here. So like practically if we have an orthogonal matrix, it's much easier to do things because the inverse is just the transpose. Okay, so we use this method here, and it turns out that the equation is actually converts into this form. Why is this true? Well, previously we already had this, but we said that if I diagonalize this matrix, then this matrix here can be written as Q times D times Q transpose. So basically I replace this thing in the middle with that form, and when I let x equal to this thing, I should end up getting this expression. So basically now it's much simpler because the elements on like the top right and bottom left are now 0, and so I can simplify it down to this. And this is in the form of a conic that you would normally be able to graph, because it would have the axis of symmetry would lie on the axes of like on the big X and the big Y axes, so you'll be able to draw them. If the coefficients are both positive, then you would get an ellipse. If one of them is negative, then you will get a hyperbola. But basically these ones would have big X and big Y to be the coordinate axes, so maybe I'll have an ellipse. Okay, and this is like, it's easy to construct this ellipse on this XY plane. But of course the original question is like, how does this conic look like on the small XY plane? Obviously this is not that great. But okay, I guess we'll look at the example first, and then we'll see how we can do it. So let's say we want to sketch this curve. So this is the same problem as above. Well, the first step is always just to rewrite this in this form with a matrix in the middle. So where did I do it? How did I choose that? So 5 and 8, so the coefficients of x squared and y squared are just the top left and the bottom right elements, and the other two elements would just be half of the 4. And so we can always write it into this form. That's the matrix in the middle. And this is annoying, so we want to diagonalize this matrix. So this is the usual process. I'm not going to go through it again, but if you diagonalize it, you can find that this is the form of that matrix. So if I've diagonalized it, And I don't like these terms because they are annoying, so I'm just going to put these things together. So I'm going to put these things together. Alright, so here remember it was inverse because this was actually not an orthogonal matrix, but if you made it orthogonal by like standardizing, so I've made it orthogonal, then in that case the inverse here is simply the transpose. So this matrix on the right is simply the transpose of the one on the left, because they have they've made it so that each of the columns is now a unit vector, and so all of these are actually orthonormal. Right? Because remember, this is a here's the explain it carefully. So like this thing here is a real symmetric matrix, and so we said it's possible to get an orthogonal matrix. It is. So this is an orthogonal matrix, so the inverse is simply the transpose. So this thing here is the transpose of the first one. And then now I want to get rid of the thing, so I want to sort of I basically want to call this entire thing here xy. And I want to call this thing here xy transpose. And that should be true because, well, the thing on the left is just a transpose of the thing on the right. And so by making that, so letting x equals to this, how did they choose that? Well, that's just in this way. Right, like xy is just this matrix multiplication here. And then you should get these formulas. And from here, you can obtain this equation. Okay. I guess like how did that happen? Well, remember we just said that we were replacing this with xy, this thing here of xy. I still have this matrix left over. If I multiply it out, I should just end up getting 4x squared plus 9y squared is 36, which is the number on the right. So this is of course something that we can very easily draw because we don't have that xy term in the middle. So we can very easily draw this. This should just be an ellipse with intercepts of plus or minus 3, 0, and 0 plus or minus 2. But of course, this is on like the big X and big Y axes, which is not what we want. We want to have the small x and the small y axes. And how do we do that? Well, actually, we need to look back at our eigenvectors from earlier. So if we actually did it properly, then the eigenvectors corresponding to these eigenvalues were -2, 1, and 1, 2. So that's just saying that one of the directions of the eigenvectors is 1, 2. So this is y is equal to 2x, and we have y equals to -12x, which is the direction of the other eigenvector. So the direction of the big X and the big Y axes are actually just the directions of the eigenvectors. So like this is your big X and your big Y axes. And so if you were to draw this ellipse, it would look something like this. Right, so like you all know how to draw on the big X and big Y axes, but now we just need to like draw in where the big X and big Y are. It's along the line y is equal to 2x, and along the line y equals to -12x. So this is approximately like how this ellipse would look like when we actually draw it. Okay. Yeah, I guess apologies if I'm going a little bit fast, but actually like well, there's a massive amount of content in this course. I can't really cover every single thing in detail. Alright, so next thing we have here is our rotations and reflections. So orthogonal matrices which we have looked at, these have a determinant that's plus or minus 1. Well, I guess we already know that Q transpose is equal to Q inverse, and so we know that Q transpose times Q is actually equal to the identity matrix. And so that's saying that the determinant of q squared is equal to 1. And so that's why the determinant is plus or minus 1. And it turns out that any eigenvalue of an orthogonal matrix has a modulus of 1. So it turns out that orthogonal matrices actually correspond to either a rotation or an improper rotation. So like first you flip it and then you rotate. So for a 2x2 orthogonal matrix with determinant 1, it would be similar to this rotation matrix. Now this rotation matrix just means that I rotate in the anti-clockwise direction by alpha. So if I have a certain point, a certain vector, then if I were to multiply it on the left by this matrix, then it will rotate by an angle of alpha. Right, so it turns out that every orthogonal matrix with a determinant of 1 is actually similar to a rotation matrix. So it's similar, and so I guess if you want to work out like what angle does a certain orthogonal matrix rotate a vector by, all you really need to look at is the trace. The trace is 2 cos alpha. And so if you find the trace of your orthogonal matrix, then you can solve for alpha, and that's the angle that it would be rotated by in the anti-clockwise direction. Well, I guess like more commonly, you'll probably get questions on a 3x3 orthogonal matrix. This is a bit trickier. So typically, there's like, typically your matrix would be similar to one of these. If 1 is an eigenvector, so if 1 is an eigenvector, we should say our matrix is similar to the first one. But if -1 is an eigenvector, is an eigenvalue, then our matrix should be similar to this second one. Now, how do we know which one it is? Well, you just need to work out whether your matrix has 1 or -1 as an eigenvalue. If it has both, then you just use the first one because that's more convenient. Because the first matrix here corresponds to a rotation by an angle of alpha with the axis of... Okay, let me say this again. So this is a bit trickier because in the 2-dimensional, it's quite simple in how we rotate. But in 3-dimensional, there's many ways you can rotate. So if you have 1 as an eigenvalue, then the axis of rotation is the eigenvector corresponding to the eigenvalue of 1. Whereas if it's similar to the second matrix, then it's an improper rotation. So you have to reflect it. You have to reflect it about the eigenvector corresponding to the eigenvalue of -1, and then rotate by an angle of alpha. So I guess like for a couple of examples, given this first one, we want to give a geometric description. Well, they already told us that eigenvalue is 1, so that's very simple. We know that eigenvalue is 1. You should probably check, well, I guess like if, usually if a question like this, it should be obvious, but like A and B here are actually orthogonal matrices. You might want to confirm that. So orthogonal means that if I take the dot product of any pair of columns, I should get 0, and the length of each column should also be 1. That'll make it orthogonal. Now, because we know that 1 is an eigenvector, then because we know 1 is an eigenvalue, we know that this is actually just a rotational matrix. So it's similar to the first one here. And so in order for us to calculate the angle of rotation, all I need to do is calculate the trace. In this case, the trace is 1. But the trace is equal to, well, 1 plus 2 cos alpha. And so 1 plus 2 cos alpha should be equal to the trace, which is 1. And so the angle of rotation is pi on 2. That's all you need to look at. You just need to look at the trace and equate that to 2 cos alpha plus 1. The solution is the angle of rotation. So if we know that 1 is an eigenvalue, it's pretty simple. And the second one here we have is, oh yeah, I should also point out the axis of rotation. Like remember, rotating by an angle in 3 dimensions is like more complicated. It needs to be about some sort of axis. So it's about the axis 2, 2, 1. That's just the eigenvalue. That's just the eigenvector that corresponds to the eigenvalue of 1. And similarly, we do B like this, except this one has an eigenvalue of -1. So in order to do this one, well, you sort of do the same thing. You find what the eigenvector is. But this is an improper rotation, meaning that first of all, we need to have a reflection followed by a rotation. So this is the eigenvector corresponding to -1. We first have a reflection about the plane given by that. So that axis of rotation dotted with this plane. So it first is reflected about it, and then we have rotation about that same axis, and the angle of rotation is given by this. Now this is a bit different, right? Because this time it's similar to the second matrix. And the second matrix has a trace of -1 plus 2 cos alpha. So -1 plus 2 cos alpha is equal to 109, which is the trace for this matrix here. So I guess like if they give you like a matrix and they don't tell you what the eigenvalues are, and they ask you what is the geometric description of the matrix, you need to first work out whether the eigenvalue is, whether 1 is an eigenvalue, and if not, then -1 should be an eigenvalue. And then you need to find the eigenvector, and then you can talk about whether it's just a rotation, this is just a rotation, or whether it is a reflection and then a rotation. Okay. Yeah, hopefully everyone's clear on that. Yeah, again, it's a bit fast because there is a huge amount of stuff in this course. Right, so I guess like the next thing we have is singular value decompositions. So the SVD. I guess this has quite a lot of applications in a lot of fields. So basically, this is just like a more convenient form for writing a matrix. I guess like for the first time today, we're looking at an m by n matrix. So like this matrix does not need to be a square matrix, unlike everything else we've looked at so far. Basically, I can write this in a nice form. So first of all, we'll talk about singular values. So singular values is just the square root of the eigenvalues of A star A. A star is the adjoint, which if you remember is just the conjugate transpose, or in the case of a real matrix, the adjoint is just the transpose. So this represents the adjoint. I should say A star denotes the adjoint. So we have A star A. So basically, it's got eigenvalues, and the singular values are just the square roots of those eigenvalues. And so it turns out that I can write my matrix in this form. So for any m by n matrix, I can actually write it in this form. U sigma phi star. And what makes this form very special is that U and V are actually unitary matrices. Remember, unitary just means that the adjoint is equal to the inverse. So it's sort of like a generalization of orthogonal matrices to complex matrices. Right, so we have U and V, and then sigma over here has got entries which are the singular values. So just now we said the singular values is calculated from A star A. Then those singular values we can, that's just what this sigma here is. Okay, pretty much like this is just the algorithm. It's pretty much something that you can just like memorize and then use it in the exam. And yeah, like I guess it's a bit tedious, but it's not really hard. It's just a bit annoying to do. So first of all, we just need to find all of the eigenvalues of A star A. We already know how to do that. The convention is to have them in descending order. So the convention is to have this sigma matrix here, right? So sigma is actually a diagonal matrix with each of the diagonal elements. Sorry, I shouldn't say it's a diagonal matrix because sigma is not necessarily a square matrix, but I'm saying like going from the top left, going to the bottom, going down, or going like bottom right, each of these values is a square root of the eigenvalue of A star A. and the convention is to have them in decreasing order, or I guess more accurately in non-increasing order. Okay, so that's how we get the sigma, and I want to find the associated eigenvectors of unit length vi. And because we actually want a unitary matrix, we actually want these to be an orthonormal set. You hope they're orthonormal. If they're not, then you need to use the Gram-Schmidt process to make it so that we do have an orthonormal basis. And so like that will make up your vector, the matrix V over here. V is the matrix of eigenvectors corresponding to each of those eigenvalues. Right, so it's eigenvector of A star A. Now, A star A itself is always a square matrix, so like all of this makes sense. Okay, and then you have this formula here to calculate what U is, and well, all of these vectors for U just make up the matrix U over here. So I guess like in terms of how we actually do this, so we found V, right? So V is like an n by n. So n by n, that's your V. And then U, we calculate by applying the matrix A to V. Well, matrix A is m by n, so it takes the vectors in V to something, it takes the vectors V, which are in Rn, to Rm. Oh, I guess I should say C. So like this is an m by m matrix. And then finally, sigma, well, it should be n by m, because matrix multiplication has to work. So so this is the size of sigma. And so the diagonal entry starting from the top left to downwards should have a value equal to the square root of the eigenvalues, and everything else should be 0. Okay. We'll just do an example for this. And some interesting results we have is that A star A and AA star actually have the same non-zero eigenvalues. We'll look at why this is good in a moment. So we have this matrix here, and we want to find the eigenvalues of AA star. So like basically this entire question is we're trying to find a singular value decomposition. But the idea is that, well, singular value decomposition, remember from above, it requires a calculation of A star A and the eigenvalues associated with it. But in this case, if I calculate A star A, you will get a 3x3 matrix, which is not good, because that's, well, it's not good, it's just annoying to work with. But instead, if we calculate A star, you get a 2x2 matrix. And a 2x2 matrix is great because you can very easily calculate what the eigenvalues and eigenvectors are. Or I guess just eigenvalues, right? Because we saw in this lemma above that no matter which order I do them in, they should have the same non-zero eigenvalues. So in this case, I just need to find the eigenvalues of A star, and that would be the same as the eigenvalues of A star A. So that's what we do. We calculate A star. That's a simple multiplication, and we should get this. And this is a very simple matrix. We can work out the two eigenvalues are 12 and 10. And so what we said above is that A star A and AA star have the same non-zero eigenvalues. So if 12 and 10 are the eigenvalues of A star A, then that's saying that 12 and 10 are the eigenvalues of AA star, so they're also the eigenvalues of A star A. And we know that, well, A star A is a 3x3 matrix, the other eigenvalue would just be 0. That's the last eigenvalue. So basically, why did the question do this? It's just that it's easier. It's easier to calculate the eigenvalues for A star. And then just transfer them over to A star A. But ultimately, we care about A star A, because that's required for this, the singular value decomposition. So I guess like next off, we want to find the eigenvectors, which is, well, very typical. We can now calculate A star A. We get this matrix here. We already know what the eigenvalues are. We know it's 12, 10, and 0. So I can just take away 12i, and I get this matrix. And from that, I can work out what the eigenvectors are. Assuming you did everything correctly, this matrix here, even though it might not look like it's it might not look like it's got a kernel that's it might not seem like this matrix has a non-trivial 0, but in fact it does. So you can just like guess something that works. I guess looking at the first line, we know that the first and third coordinate need to be the same, so let's just set them to be 1, and then just choose some random value for the second one to make it work. I guess looking at the second row, we probably want the second coordinate to be 2, because then 2 times -2 plus 1 times 4 will give us 0. Okay, so then we get this is the eigenvector. Okay. So next we have over here, we do exactly the same thing for lambda equals to 10, and we can do the same thing for lambda equals to 0. Oh yeah, in case any of you are like confused with what the t is, well, I guess like that's just saying that this is like all of the eigenvectors. You don't need to write that. We just need one eigenvector. So I can take t to be 1 if I want. We just need to have one eigenvector that works. But okay, so I guess the next part of the question is to actually find a singular value decomposition. So far we've found the eigenvectors. So if we go back to the process above, we wanted to put it in this form. So we already know what sigma is, right? We know the eigenvalues are 12, 10, and 0. So sigma will just need to have square root of 12 and square root of 10. And then we found the eigenvectors, so that will just be the columns of V. Actually, we need to have an orthonormal, we need to have these 3 vectors being orthonormal, then it would be the columns of V. So all we do here is we normalize each of them. I think in this case they are already orthogonal. If not, you will need to use the Gram-Schmidt process to make them orthogonal. So all of them have been normalized, so now all of these, so this is now an orthonormal basis for R3, and that's just our matrix V. And to get U, we just need to substitute it into this equation. So for V1, it's got an eigenvalue. So remember, this is lambda I is just the eigenvalue corresponding to it. Root lambda I is just a singular value. So you might also see this written as 1 over sigma. So it's a bit annoying, but A, like this is our matrix A. This is our 1 over the square root of the eigenvalue that corresponds to this eigenvector. The eigenvector has to be normalized, and then we get the vector for U. And then we should get and similarly, we do the same thing with our other vector, and we should get U2. Note that we had 3 eigenvalues earlier, right? We had 12, 10, and 0. We don't care about the 0. Obviously, we can't do 1 divided by 0. So we're only doing this process for the non-zero eigenvalues. And remember, the whole point of this SVD decomposition is that the matrix U and the matrix V should be unitary matrices. So once you get these values for U, just to sanity check your answer, you should make sure that these 2 vectors here are actually they're actually orthonormal. Right? Obviously, they both have a length of 1. In this case, you can check that, and if I dot them together, obviously you get the 0 vector. So in fact, U1 and U2 here are orthonormal, and so the matrix U, remember U is made up of U1 and U2, would be a unitary matrix. And like V, made up of these matrices, would also be a unitary matrix. So if we put all of that together, this is U. So that's just, that's just U1 and U2 put next to each other. And then V is just those 3 vectors in those 3 vectors V put together into a single matrix. And then finally, sigma should have root 12 and root 10 being the singular values. And the dimensions of sigma, you don't really need to memorize this, but the dimension is just so that the matrix multiplication makes sense. The number of columns in sigma obviously needs to match the number of rows in V, otherwise we can't multiply them, and the number of rows in U needs to match the number of columns in sigma. And so it's clear that this sigma is of this size. So we have root 12 and root 10 on the diagonals, and then 0 everywhere else. Some things to watch out for is that like everything should correspond. Like the eigenvalue 12 should correspond to this eigenvector, and then this vector in U is obtained by applying that formula to this vector. Yeah, so I guess like technically you could switch some of the orders around, but this is a convention. The convention is to have sigma written so that these singular values are in non-increasing order. So it's root 12 and then root 10, not the other way around. So this is a conventional form, and so you should do that as well. Right, so you have U, sigma, and V. Like the formula here actually has V, free adjoint. Remember this is actually this is a unitary matrix, so yeah, so it's also just the transpose, the conjugate transpose. But you can just leave it in this form. You won't need to like actually multiply them, because again that's a bunch of work, and of course we won't multiply them because you just get A again. We just leave it in this form. So like this is like a simpler way to write A, because we have unitary matrices which are convenient. Okay, I guess the next section we have is on the Jordan blocks. So first of all, we just define what the Jordan block is. So if we have a K by K Jordan block, that's saying that we have a K by K matrix where the main diagonal is lambda, so a certain eigenvalue, and then we have 1 on the diagonal that's above the lambda. Okay, so like why do we have Jordan forms? So like earlier we thought that earlier we looked at diagonalizable matrices, and we thought that that was useful. Diagonal matrices help in many ways, but many things can't be diagonalized if we don't have n linearly independent eigenvectors. But it turns out that every matrix can be written into a Jordan form. In fact, everything has a unique Jordan form, and the Jordan form is related to these Jordan blocks. So it can be shown that every matrix can be decomposed into this form. This is just like your diagonalization. In this case, J is a matrix of Jordan blocks joined together by direct sums. I guess we'll see that a bit more in the next few slides. Right, this is a Jordan block. In this case, J here is a Jordan matrix. So not the same thing. Okay, so this is what we mean by that. So say we have a Jordan block that has a size of 3, so that's saying it's 3 by 3. And instead of lambda, this time we have -4. That just means we have -4 on the main diagonal, and we have values of 1 on the diagonal above. If we have J 4, 0, that means that we have a 4 by 4 matrix. The main diagonal is 0, and the diagonal above is 1, like so. It turns out that we can actually take powers of Jordan blocks in this way. You pretty much I think you very rarely need to do this. It's not a very convenient method anyway. You probably won't really see this much. But this is just saying that we can actually very easily calculate, it's saying we could calculate powers of a Jordan block, as similar to how you can calculate the powers of a diagonal matrix. Okay, so pretty much this is a process. We start with lambda n on every diagonal, and then for the next diagonal we just do n choose 1, lambda to n minus 1, and so on. So basically we have those binomial coefficients, and the power of the lambda is going down by 1. I think the pattern is pretty obvious just by looking at this. Okay. And then we just need to define the direct sum of matrices. So when we have a couple of matrices, the direct sum just means that I put them together on like a diagonal like this, and I fill out everything else with zeros. So yeah, well, I guess in this matrix, each of these elements here are actually matrices, right? They're not numbers. So I guess this means that if I have the I don't know, if I have like the matrix 1 and I have the matrix, let's say 2, 1, 1, 1, then if I want to find the direct sum of these two, then I will now have a 3 by 3 matrix. I'll have this matrix there, and then I'll have the other matrix here, and then everything else would be zeros. That's what we mean by doing a direct sum. Okay. Well, I guess like the only time we really look at this for 2501 and 2601 is with Jordan blocks. So, oops. So say we have J23, that's just the red bit over here, and we have J45, that's just this bit here. Like remember, we have 5 on the main diagonal and 1 on the diagonal above. So if I want to do a direct sum, I just like put them together like this, as we did above, and then fill out everything else with zeros. And this is what we call like a Jordan matrix. So a Jordan matrix is just the direct sum of Jordan blocks. Okay, so and it turns out that if we take, so if I have a direct sum of Jordan blocks and take it to the power of n, then actually I can take the power of n for each of the Jordan blocks individually, and then take the direct sum of all of them. I don't think you really need to use this either. So I guess like we won't worry too much about that. Okay, so then we talk about generalized eigenvectors. So earlier we've talked about well, like eigenvectors. Like eigenvectors don't have to have a geometric multiplicity of n. So like it turns out that some of them we need to be looking at generalized eigenvectors. So what it means to be a generalized eigenvector just means that if I so a generalized eigenvector with an eigenvalue of lambda is any non-zero vector that satisfies this property. So it might not be in the kernel of a minus lambda I, but it could be in the kernel of a minus lambda I squared. Then I would say is, so if it's in the kernel of a minus lambda I squared, I would say is a generalized eigenvector corresponding to that eigenvalue lambda. But it would not be an eigenvector. Okay, so so I guess like normally when we have, so I guess like why this is a generalized eigenvector is that normally an eigenvector satisfies this, which is just the case where k is equal to 1. A generalized eigenvector might have a higher value for k. Okay, so it showed that the matrix, for the matrix C over here, V is a generalized eigenvector corresponding to lambda is equal to 5. So all we really need to show is that a minus lambda I to the k times V is equal to 0. That just means that if I apply a minus 5i, I want to calculate this. If it's 0, that means that this is an eigenvector. If not, then I want to apply the square and see if it's 0. If not, I want to apply the cubed. Since the question tells us it's a generalized eigenvector, it should eventually go to 0. And it turns out that you should never need to apply this more times than the algebraic multiplicity of this eigenspace. So actually, if lambda is equal to 5, this is a 3 by 3 matrix. So the algebraic multiplicity is at most 3. So that means that I need to apply a minus 5i to it at most 3 times. And if you apply more than 3 times and you still can't, so if you apply 3 times and it's still not 0, then most likely you've done something wrong, or the question's wrong. Yeah, so you won't need to apply it more than 3 times. That's the most. Okay. So okay, we do that. C minus 5i is this one, and then we multiply it by V. You can do that calculation yourself. You should get this vector, which is obviously not the 0 vector. So in this case, V is not an eigenvector with eigenvalue 5. But if I apply it a second time, it is equal to 0, which means that v is in fact a generalized eigenvector, which lives in the kernel of c minus 5i squared. Okay. And so like earlier we have the eigenspace for an eigenvalue. Here we have a generalized eigenspace. So we say here v is a generalized eigenvector with an eigenvalue of 5. Okay. That's what we have here. So generalized eigenspace is a set of all generalized eigenvectors. So it's the kernel of a minus lambda I union with the kernel of a minus lambda I squared, and so on and so on. In fact, we can actually like simplify this. Like if this is like finite dimensional, I can say this is just the kernel of no, hang on, that's not true. Okay. Yeah, I guess we'll get to that point a little bit later on. I think it's on another slide. Okay, so yeah, Jordan matrix we said is a direct sum of Jordan blocks. And one of the important properties is actually uniqueness. Every matrix A has one unique Jordan matrix up to some permutation of the Jordan blocks. What that means is just that, say we have, I don't know, earlier we had this Jordan block. So a certain matrix might have this Jordan block, or maybe it would just have these two blocks sort of swapped around. I can swap the two blocks around, but otherwise like it should have the same structure. So it should have the same structure of this 3, 3, and 1, and this other structure of the 5, 5, 5, 5, and the 1, 1, 1 on top. So everything has a unique Jordan form. Okay, so some very important properties here. So it turns out that the kernel of a minus lambda I is a subset of the kernel of a minus lambda I squared. This shouldn't come as a surprise to you, because if for example v is an eigenvector, then we know that a minus lambda I times v is equal to 0. Well, then it shouldn't come as a surprise that if I were to apply a minus lambda I to it again, so if I apply it again, it will still be 0. So any v that is an eigenvector will also be in the kernel of a minus lambda I squared, and so on. Like anything that's in the kernel of a minus lambda I squared will also be in the kernel of a minus lambda I cubed. So that's why it's a subset. And so that also means that in general, the nullity, if I call it dk, so the nullity of a minus lambda I to the k, the nullity should be non-decreasing. This just follows from the being a subset. Okay, so I think like those first 2 points are probably a bit more intuitive. And the third point here is less clear, but it's quite useful as well. So this is saying the difference between the dimensions of this to the power of 0 and to the 1 needs to be greater than the difference between the 2 and 1. So this is saying that the nullities must not decrease is number 2, and the difference in nullities does not increase. To make that clear, we'll do some examples later on, and yeah, hopefully that'll become more clear. Okay, as we mentioned earlier, we don't actually need to check forever to check if something is a generalized eigenvector. You can actually stop when the nullity is equal to the arithmetic, the algebraic multiplicity. So I guess one of the problems is like finding these Jordan chains. So basically our goal is to like actually compute the Jordan forms. Like how can I put a matrix I have into the Jordan form? Well, the task is like we need to find all of those generalized eigenvectors, which is a bit difficult. Practically in your exam, if you were to do this, you would probably just like try to guess something that's an something that is a generalized eigenvector and sort of try and get it to work. But otherwise it's quite difficult. Or usually the question might tell you. So let's say that somehow we manage to find a vector that is a generalized so let's say we find a generalized eigenvector such that I need to apply a minus lambda I to it k times in order to get it down to 0. Then the way we construct the Jordan block, so I guess like the issue here is, okay, so I guess I really want to put it into the Jordan block, right? But in order to get a Jordan block, we need to have some sort of matrix that is a change of basis, right? It's sort of like diagonalization. When we have diagonalization, we need to, we say that A is equal to P inverse. And the P here is the matrix containing the eigenvectors for each of those eigenvalues. So here we're doing a similar thing. If we find a vector here that is a generalized eigenvector, such that when I apply a minus lambda I to it k times is equal to 0, I need to keep track of these vectors from v1 to vk. But like the order we should, later on the order that we need to put them in, when we put them inside the matrix, is in the reverse order. So it's always the eigenvector comes first, and then comes an eigenvector that is in the kernel of a minus lambda I squared, and so on. And so this v1, which is like which lives in the kernel of a minus lambda I to the k, is actually in the last position. So it's actually over here. This will become more clear in the next few slides. So yeah, I think it's probably better if we do the example, and then that will make it more clear. Okay, so basically this is a question. We've already done the first part, it's just computation, so we won't do that. Now, what I want to do is calculate the algebraic and geometric multiplicities. I'll do that, and then the second part is to actually put it into the Jordan form. I guess like part 3 is the main part that we're trying to cover here. Okay, so first of all, we want to write down the eigenvalues and the algebraic and geometric multiplicities. So I guess like from earlier on, so in the previous part you guys might have forgotten, but we calculated this one. And we said that this one here is the 0 vector. And this one here is not 0. And so basically from earlier, we concluded that this vector here is a generalized eigenvector that lives in the kernel of c minus 5i squared. In other words, that's saying that the eigenspace corresponding to the eigenvalue of 5 has a dimension that is at least 2, right? The geometric multiplicity is at least 2. The algebraic multiplicity is at least 2. So we know that 5 and 5 are 2 of the eigenvalues, and then we can just use the trace to work out the last one. So the trace here is 13, so the last eigenvalue must be 3. And so obviously we worked out that the algebraic multiplicity of this one was just 1, and so hence the geometric multiplicity is also 1. And then here we worked out the algebraic multiplicity is 2, but the geometric multiplicity is 1, right? Because this vector v here, it was not an eigenvalue; it was a generalized eigenvector. So that means that it's the eigenvector. So that means that the geometric multiplicity of the eigenvalue 5 is only 1. Because it's actually a generalized eigenvector for it that is not an eigenvector. Okay, so yeah, so like work that out. So finally, we need to explain part C, which is actually putting it inside the Jordan form. So to do this, we're going to find the eigenvectors first. So for the eigenvalue 3, we have this eigenvector. For the eigenvalue 5, we actually already did it. So like, remember we had this generalized eigenvector, and when you apply c minus 5i to it, we get this one, and then when you apply it again, we get 0. So actually, not only do we know this is a generalized eigenvector, we actually know that this one here is also an eigenvector. Okay, so we actually know that this one here is an eigenvector. And this one here is a generalized eigenvector. So I guess like typically if you get in an exam question, if you know like what one of the eigenvectors would be, if you know what one of the generalized eigenvectors would be, then you can like use that, and along the chain you will get other generalized eigenvectors in other dimensions. In other well, like c minus 5i to the k. And this one here is the one that we just found on the previous page, which is using the typical method of finding the kernel. Okay, so basically here we've got two eigenvectors and a generalized eigenvector. So in terms of like the blocks, so for the block with 5, we have like, this is the block. So we have an eigenvector, this is a Jordan block with a size of 2. And here a Jordan block with a size of 1. That's how we got that. And then, okay, obviously you could interchange these if you want. This is just the way I decided to do it. You could swap the 3 and the other block if you want. And then the matrix P over here, like how do we get this? Well, the negative 1, 1 is the eigenvector corresponding to 5, and the 1, negative 2, negative 3 is the generalized eigenvector. So if you remember earlier, on the earlier slide, we said we need to reverse the direction. This is exactly what it is. Right, we need to reverse the direction when we put it inside the matrix. If you don't do that, the answer is actually wrong. So the order I put it is that the eigenvector comes first, and then the generalized eigenvector. Or if there's like more of them, then like we just go in reverse order. The 3 is simple. That has one eigenvector. Okay, so I guess this is a case where like the so in this example, the eigenspace of the lambda of like the eigenvalue 5 was had a dimension of 1, right? That's why we need to have the generalized eigenvector. In another case where let's say the eigenspace of the lambda of 5 actually has a dimension of 2, then in that case your Jordan block will just look like this, without the 1 on top. So like, this is a case where the eigenspace corresponding to eigenvalue 5 actually has 2 linearly independent eigenvectors. So one way to think of Jordan forms, like this is just a generalization of diagonal matrices. If your vector actually has n linearly independent eigenvectors, then actually the Jordan matrix here would just be the same as a diagonal matrix. But in this particular example here, for the eigenvalue 5, we actually only have one linearly independent eigenvector. That's why we need to use a generalized eigenvector, and the block would have a size of 2 instead. Okay. So let's see, do we have time for this? Yeah, I guess like maybe we would skip that example. If we have time, maybe we can come back. Okay. Well, I guess like one point that I should point out here is that the direct sum of generalized eigenspaces of any matrix always span Cn. So I guess like that. I guess another thing we should say is that the dimension of the number of generalized eigenvectors you have should always equal to the algebraic multiplicity, and hence as a result, the direct sum of all of these should span Cn. Okay, so one of the useful results with Jordan forms is that it completes a similarity invariant. So earlier we've seen that trace and determinant, those are similarity invariant, so it means that if we have similar matrices, meaning in this form, they will have the same trace, they will have the same determinant. But it turns out that but just because two matrices have the same trace and the same determinant doesn't necessarily mean that they are similar. So in order to check if two matrices are actually similar, you need to check their Jordan forms. So two matrices are similar if and only if they have the same Jordan form with a different arrangement. So basically we will need to find the Jordan matrix for anything. So if something has like so we just need to find the Jordan matrix. For example, we might have two I don't know, so something like this. So let's say for matrix A, the Jordan form is like this, and for matrix B, maybe the Jordan form would be something like this. In this case, like these two matrices are not similar because they have got different Jordan forms. A has a Jordan block that would be like this, whereas matrix B would have a Jordan matrix that looks like this. So I guess like in this case, both of them have the same eigenvalues, they have the same determinant, they have the same trace. A lot of things are the same, but they're actually not similar because when I put them into the Jordan form, I find the Jordan matrix, and Jordan matrices are actually different here. One of them is like so the first one is a 2x2 Jordan block, whereas B is a direct sum of two 1x1 Jordan blocks. So this is a 0 instead of a 1. Now, like what you would see is like B would have B is like diagonalizable, but A is not. A would need to have a generalized eigenvector. Okay, and yeah, Jordan forms given the nullities. So this is going back to one of the things we pointed out earlier. We said that the nullity is something that is non-decreasing, right? Like if something is in the kernel of b minus lambda I, it will also be in the kernel of b minus lambda I squared, and also be in the kernel of b minus lambda I cubed. So like these nullities here, they are non-decreasing. And the other thing you also remembered is that the difference between them is not increasing. So the difference here is 3, and the difference here is 1. The differences is non-increasing. Okay, so find all the possible Jordan forms of B. In this case, we use an onion diagram. I think maybe in class you would have used diagrams of like a pile of blocks. They're pretty much the same thing. So this is the block that this is the diagram that we use to represent it. So we know that the nullity is this is 5, so that's saying that there are 5 eigenvectors. These are the 5 eigenvectors. And then we know that the nullity of b minus lambda I squared is 8. Now obviously the 5 eigenvectors also exist inside here. So we've already got 5. That means that there's 3 other linearly independent generalized eigenvectors that are inside the kernel of b minus lambda I squared, but are not inside the kernel of b minus lambda I. So 5 plus 3 adds up to 8. That's why we have 3. And then we see that there's again all 8 eigenvectors in the nullity of b minus lambda I squared will also exist in the nullity of b minus lambda I cubed. But this is a 9, so that just means that there is one more vector that is inside there. So that's the diagram. So the question is asking us find all the possible Jordan forms. So the question has told us that it's a 10 by 10 matrix. So far we've accounted for 9 generalized eigenvectors. So there's one more. The problem is that like that one more eigenvector, it could have the same eigenvector lambda, but it doesn't necessarily have to. It could have a different eigenvalue entirely. I suppose that's the easy case, where the 10th eigenvalue is not lambda. If the 10th eigenvalue is not lambda, then well, that's perfectly fine. That just means it will have a block by itself. it would have a 1 by 1 block by itself with eigenvalue, let's say mu, which is not equal to lambda. And then the Jordan matrix itself will just be this direct sum. Where do we get this? Well, from the diagram above, so we have got one Jordan chain that has a length of, that has got 3 vectors in it. So like 1, 2, 3. And then we have got 2 other ones that have got two vectors and 2 other blocks with 1. So that's why we have one of them that has 3 vectors, 2 of them that have 2 vectors, and then 3 of them that have, 2 of them that have 1 vector. And then this one is for the other eigenvalue we have. Okay, and then that's the first case, if the 10th eigenvalue is not lambda. The second case is actually like trickier. What happens if the 10th eigenvalue is also lambda? Well, if it is like a generalized eigenvector, it can't live inside any of these kernels because we already know what the nullities are. So if it was to exist in it, it would have to be in the kernel of b minus lambda I to the 4. And so if we have something else in b minus lambda I to the 4, we can draw it like this. That's just saying I have one more here that goes into it. And so all I need to do is change it from a block of 3 to a block of 4. And I'll be done. In this question, it's fine. But sometimes you need to be a little bit careful about that. Which is, earlier we said that the difference in the nullities have to be non-increasing. So in this case, it changes to 10. So the difference between here is 1. That's fine. It's non-increasing. But it actually can't be the null. So I guess here we assume that it's in the kernel of b minus lambda I to the 4. It actually has to be to the power of 4. It can't be any other power. It can't be to the 5 or to the 6, because that would break that rule about it being non-decreasing. So I guess like if instead we say that this is 9, if this is like 9 and this is 10 for the next one, then this difference will be 0, and if this difference is 1, and this is not allowed, because these differences are, well, it decreases from 1 to 0 and it increases again. That's not allowed. The differences are non-increasing. It can't increase from 0 to 1. That's not allowed. So that means that if we have another generalized eigenvector with eigenvalue lambda, it needs to exist in the nullity of b minus lambda I to the 4. So this is the only other case. We can't have any other example. Okay. Yeah, so I guess using that same rule about the difference in nullities being non-increasing, sometimes they can give you a case and ask you, like, is this possible or is it not possible? So if they ever ask you this, there's just 2 things you need to check. First of all, are these non-decreasing? Well, yeah, it's non-decreasing. It's never going down. That's the first rule. And the second rule is looking at the differences between them. This difference is 3, this difference is 1, this difference is 3, this difference is 0. That difference needs to be non-increasing, which is not true, because going from 1 to 3, that is increasing, so that's not allowed. So this is not possible. I guess like intuitively why this has to happen is just because of what we had earlier. Actually, I guess not. Right. Okay, so I guess in this case over here, I want to find the nullity of these. So, okay, I guess we can just do like one of them. The other one will be the same. So this is like the Jordan matrix. These are all of the Jordan blocks corresponding to an eigenvalue of -4. So we're trying to find what is the nullity of a plus 4i to the k. So remember, for each linearly independent eigenvector, it should have its own block. So I guess like if you use a block diagram, one way to think of this is that we have a block that has a size of 2, and then we have another. So like these are all 2s, So we actually have 3 separate blocks, and each block has a height of 2. What that means is that all of the vectors on the bottom, these are all eigenvectors. These are all eigenvectors. And the ones on the higher column, these are all generalized eigenvectors corresponding to a plus 4i to the power of 2. And if there was like a higher block, for example, if there was like if one of them was like a size of 3, then this would be in the kernel of a plus 4i to the power of 3. And so in this case, we're trying to find what is the nullity for different values of k. Well, if k is equal to 1, that's just saying we're looking for the nullity of a plus 4i, which is just the eigenspace of a with eigenvalue -4, which is just like the bottom bit over here. So there's like 3 eigenvalues for a, and so for k is equal to 1, the nullity of a plus 4i would be 3. And if we have k is equal to 2, that's saying we're looking for all of the linearly independent eigenvectors that are in the kernel of a plus 4i squared. Well, we said that anything that's an eigenvector will also be in that kernel. In addition, we have these 3. So in total, we have 6. And based on this diagram I have, if we had k is equal to 3, I would have another one. I would have 7. But in this question, that thing doesn't exist. Okay. Yeah, so we have 3, and then we have 6, and it will stay at 6 no matter how big k becomes. Okay. Alright, good. Okay, I think I can actually finish on time. So next up, we have an exponential of a matrix. So the definition is quite simple. It's just the same definition as as like the Taylor expansion for the exponential in the real number case. So in this case, we have a matrix. We just need to do the sum. And it might not seem obvious, like, actually, I should say it's not simple to calculate this in general. In fact, it's quite difficult. And a lot of the properties that you usually expect with the real exponential function, mostly they still apply, but sometimes there's some conditions that you need to be careful about. Like normally you might think if I multiply together two exponentials, I can just add those powers together. But in fact, with matrices, you can only do this if the matrices commute. And you can prove this using like the binomial theorem with it. If you can commute, then you can sort of switch things around. But yeah, it turns out that we can only do this if the a and b commute. I guess like even further, we can actually say that if they commute, then the exponentials also commute. That's of course obvious because, the sum of matrices is commutative, so I can switch these around, which must mean that I can switch these around as well. But that's only true if the matrices can commute, right? Like normally we know that multiplying matrices together, we can't just commute them. But in this case, you can if a, b commute, then exponentials also commute. And the product is equal to the exponential of the sum. The inverse of exponential of a is just the exponential of negative a. And when I differentiate the exponential matrix, it turns out that it works just like how you expect it would behave when you differentiate the real case. So we get this, and in fact this also commutes. So in general, the exponential matrix actually commutes with any power of the matrix itself, which should be obvious from this sum, because obviously a to the k commutes with a to the power of m for some m. So that's why we can do this. So the exponential matrix commutes with powers of that matrix. Okay. Commuting them is quite tedious. Generally there's probably some, I guess like calculating matrix itself is very hard unless it's like a special matrix that makes it somehow easy to calculate. Generally you shouldn't need to. I guess like this slide here tells you how you can do it, but I guess we're not really going to bother. You shouldn't get assessed on this. So pretty much we'll skip this. I guess like this is one useful property. So I guess like this is saying like how you would calculate it if you really wanted to. But it's basically saying that to calculate the exponential of a matrix, I can actually change the basis. In this way, I change the basis, and then I just need to find the exponential of that matrix with respect to a new basis. This is true because taking the exponential is just taking a power series, and if you imagine taking this thing to the power of k, you actually get like p times b to the k times p inverse. You've probably seen that in first year. If not, you can like try thinking about it, but that's the case. And so the idea is that it's actually easier if you take the exponential of a Jordan form. So the easiest way to actually find the exponential matrix, if you really wanted to, is to first convert the matrix to the Jordan form, and then take the exponential. And it ends up being in this, well, I guess like relatively simple form, which you shouldn't really need to do, because it's really tedious. Okay. Yeah, as in the interest of time, we'll probably just like yeah, maybe I'll do this yeah, I think this you won't really need to do this one, so I'll just skip this example. But this is just applying this thing here, which is saying to calculate the matrix exponential, I just need to convert it into the Jordan form. So I convert it into the Jordan form like this, and then I can calculate the exponential of the Jordan form using this sort of process. And we get this. But okay. So more importantly is this column technique. So often we don't want to actually calculate the entire exponential matrix because that's, well, it's very big, it's not necessarily useful. Often we might want to calculate just something like this. We might just want to calculate the matrix exponential multiplied by some sort of generalized eigenvector. So it turns out that if V here is a generalized eigenvector, then the formula for multiplying it on the left by the matrix exponential is given by this formula here. So basically we have this this scalar e to the lambda t, and then inside we multiply by each of those generalized eigenvectors with these coefficients that are like very similar to well, coefficients for Taylor expansion of the exponential. Yeah, like, I guess this formula still looks a bit confusing, but generally the eigenvectors you look at might only have this might be like, as often like if V1 lives in the kernel of a minus lambda I squared, then really this cuts off here, and you really just need to compute this, which is not very hard. So this is saying that if you want to calculate the exponential times a generalized eigenvector, this is probably the process you should go through as opposed to actually finding the matrix, because that's very annoying. Okay. Problem is that V1 does have to be a generalized eigenvector. So if it's not a generalized eigenvector, you'll need to write it as the linear combination of generalized eigenvectors, which should always be possible because we said that eigenvectors always span the whole space. So it's possible, it's just a bit tedious. So the application is to solving homogeneous systems of differential equations. So let's say we have this equation here. Oh, sorry, we have this differential equation. It turns out that the solution is equal to this. Well, I guess this should make sense because if you differentiate it here, we know that when we differentiate the exponential matrix, we just get a times the exponential of TA. And like to see here, it's just so that it satisfies the initial condition. So this is saying that if I want to calculate, so like let's say with this example, if I want to find the solution to this system of differential equations, well, I just need to find the exponential matrix multiplied by C, where C is the initial condition. In this case, it's V. So all I need to do in this case is I want to calculate e to the ct multiplied by V. Right, so I don't want to calculate the entire matrix. I don't care whether I have the entire matrix, I just need to calculate the product of the matrix with V. And V here is nicely a, so V here is actually a generalized eigenvector, because we know that if we apply c minus 5i to it twice, we get the 0 vector. And so we can just use the formula we had above to calculate the exponential, like this. So in this case, I want to calculate this, that's the solution. So what I need to do is take out the eigenvalue. The eigenvalue is like 5. So we have e to the 5t, and then this is the generalized eigenvector. This is the eigenvector you get after applying a minus 5i to it once. So that was our chain. And that's simple. And then we just like put them all together. And this is the solution. That's all we needed to do to solve the equation. Yeah, so like if it's more complicated, maybe there could have been another block, but doesn't. Maybe it could have been like a generalized eigenvector where k is equal to 3. It will be a bit more complicated, but you will still follow the same method. I'll just add on another term here. Okay. So I guess like then we have a non-homogeneous system of differential equations. So if we're looking at this example instead, so it's non-homogeneous because we have an extra term over here. Typically the way to solve this is to make the substitution y is equal to e to the t c z. Pretty much every question you just do the substitution, and if we sub it in, then we'll get this. And then you realize that some of the things cross off, and actually we will end up with just this equation. Okay, so I guess like the right hand side here is again just a matrix. It's a matrix exponential multiplied by w. Again, we're given that w is a generalized eigenvector, and so pretty much we just do the same process as for the previous question. We know w is a generalized eigenvector, so first I want to work out what it is. It's actually a generalized eigenvector with k is equal to 2, so I need to apply it twice in order to get it down to 0. And so when I apply the matrix exponential to it, I just take out e to the 5t, and then I have the first term, that's the generalized eigenvector, and then this is the next one in the Jordan chain, and I have the t, because that's the formula for this sort of process. Okay, but actually the thing I want to calculate is e to the negative tc. Right, now e to the negative tc, it seems like it's harder to calculate. We didn't know how to calculate e to the negative tc. But actually, if we calculated e to the tc, all I need to do now is change this t to a negative t. That's very simple. To calculate the inverse of like this matrix, it's very easy. I just need to change it to every time t appears, I change it to a negative sign. Whenever t appears, I change it to a negative sign. And so this is e to the negative tc times w. And going back to the formula, I just substitute that inside, I get this. The e to the 5t cancelled out with e to the negative 5t. And then we just integrate it and we get this answer. And in this case, there's infinitely many solutions because we actually can't have any constant of integration here. If the question gave you an initial condition, like they say initially y is equal to a certain vector, then there'll be a unique solution. But in this case, we have a general solution. That's why we've got c over here. If they gave you a condition, then you can sub that in and then you can find a value for c. And yeah, that would be fine. But actually one more problem, like this is a very tedious thing to do because we've actually solved for z, but we haven't solved for y. Y is actually e to the tc times z. So we have found z, now I need to find e to the tc multiplied by z. So we get this, and again we need to multiply these matrix exponentials. But actually we already realized from before that this is a generalized eigenvector and this is an eigenvector. So like we can apply the same process as earlier. So like this first one here, I will need to use that expansion. So I'll get this. And the second one over here, here it's an eigen vector, so I'll just have one term. I just need to multiply it by e to the 5t. And we still have one more term here. I guess like this depends on what the c is. If you have a nice initial condition, then okay, you can do it easily. If not, this question can actually be quite annoying because you have to express c as a linear combination of generalized eigenvectors in order to evaluate this product, which is also quite horrible to do. So like you hope c is something simple. Okay. Yeah, I guess like reordering this stuff, you can do that yourself. So the harsh reality is that if we knew what c was, so if the question gave you the initial condition c, then you might have to actually do another Jordan chain in order to deal with it. We have to work out like whether c is a generalized eigenvector. If it's not, you need to write it as a linear combination of generalized eigenvectors, and then you need to have Jordan chains corresponding to each of those eigenvectors, and then you can apply the matrix to each of them, which would take us a very long time. Okay, I guess like that's pretty much the end of our revision seminar for Maths2601. I guess I apologize if I had to go a little bit fast at times, but as you all know, this course is like massive. There is a huge amount of content to cover. So yeah, I guess like thank you guys for listening. We will finish off there then.